I increased it up to 50 gigabytes. So if you want 100 gigabytes, please tell me, and I will try to increase the quota. Okay, so let us finish off from last week. So last week, is it too large? Okay, so last week we talked about polygamma model, which is a model not for chat purposes, but for industrial purposes. So if you have a machine or some edge machine, you want to input some AI component, you should use polygamma instead of a fully sized chat model. Okay, so last week we talked about the model and but have not talked about the fine-tuning strategies. So essentially we know how Google trained polygamma. They used large-scale cloud TPU clusters and but you only have one GPU, maybe two. So perhaps fine-tuning still need some kind of specialized method like LoRa we have introduced. And unfreezing the eye, what I mean by unfreezing the eye is if you look closely to the polygamma model, you have the vision encoder. And if you're going to fine-tune the task of, say, medical X-ray, you want the encoder, the vision encoder, to learn about what say, a tumor looks like. So, because if it never seen a lung tumor, it will never know that what a lung tumor looks like. It may just recognize the lung tumor as some generic lung features. So, it is quite important when you do fine-tuning, you unfreeze the vision encoder, which allows the vision encoder, the SIGLIPs, to actually learn new filters, and it learns to detect what a lung cancer is. However, this of course costs you many gigabytes of memory, and the problem is if the model weights alone takes up, say, 12 gigabytes, and the gradient also takes 12 gigabytes, and so on and so on, it might cause, at the end, a very large gigabytes. So for different GPUs, you have different kind of VRAM to choose from. But as you might have already known, we have introduced LoRa as an effective method to train the GPU. And with this technique, you can feel very comfortable training, fine-tuning this model and using this in your project. So I think I'm not going to go through the calculation here again. I think for each week I've tried to go through this calculation, but I think at this point I'm confident you can do this calculation on your own. So I think I will skip this part. So for the precisions, it is I want to introduce a term called BE-flow 16. So BE-flow 16 is the recommended way for stability if you are going to do some fine tuning. VFlow16 actually refers to a class of numerical type that you can use during fine tuning. So I think you can recall what is a flow 23 is. Can anyone answer what is a flow 32? Flow 32, what is a flow 32 precision? Okay, it refers to a digit with 32 bits that you can then have 32 bits, so it is flow 32. So the original paper used flow 32, but VFlow16 works well in practice. So the B refers to the VFlow16 refers to have the same range of flow 32, but with less digits. So it's more. So the range fits, but you still have you still have the accuracy, but not as, but do not use up as many digits as flow 32. And the learning rate, you can try different learning rate in the project, but I think it is recommended you start with a low learning rate to avoid the catastrophic forgetting. So the input of polygamma is actually quite different from what you have learned before. So what you have learned before is a chatbot, chatbot-like input. So you input text, and with some specialized tokens, say tools tokens, and perhaps some special tokens like system tokens. Okay, so in polygamma, it is quite different. It requires a rigid input format, so you have to follow the systematic way to input into the model. So it requires you to have some image tokens, a task prefix that we will talk about later, and a separator. This /n is the separator, and also a target suffix. So the new line is one token, and it acts as a critical mode switch from understanding to generations. So omitting it, it will produce garbage output. It is fairly similar to the token to the user and assistant and system token before, but this particular token does not have the angle bracket and angle close bracket. It's just use a /n separator. And during training, it compute only the cross entropy loss only on the suffix, so only on the answer tokens. The training on the prefix tokens weighs compute, and it can corrupt the task prefix understandings. So it is very important that you know what you're actually training on. Be careful on when you're computing the actual loss function. So because the format is very rigid, so you have to read the actual documentation very carefully. And the model is extremely sensitive to prefix phrasing, like training on detect car and test with find cast grades the performance due to the distribution of shifts. So you can see training the polygamma model actually took quite an in-depth understanding of what token is and what the loss function is. So it's not as difficult, it's not as easy as you think if you pick this as your project title. So for this reason, I did not provide any code for this model. But if your group decide you want to train this, we can have a discussion, and I think you might need a special consultation section if you try to train this. And the training structure is also it's not as simple as you might think. So just to introduce the tokens, it have pad tokens like before, and beginning of sentence token, beginning of sequence token. These tokens are very similar to a chatbot, but of course it is not a usual chatbot that you have seen. And this, of course, the special token is new line separator. It separates the task prefix from the target suffix in the input format. And also it has an image token. It's a repeated fixed number of times, depends on your image resolution and patch size to the prefix input, and represent the position of the image embeddings. And also there is a location tokens, which is used to normalize the bounding box coordinates in a task like object detection and segmentation. So what I mean by that is object detection bounding box. I think you have seen this in the last semester. Object detection bounding box. Okay, so you might have already recognized these kind of boxes. So for each of this is a box, right? But you have a location, X location and Y location to actually draw out this box. So for this polygamma model, it uses these sorts of tokens to locate where the object actually is in the image. So these are the location tokens, and also the segmentation tokens. So the segmentation tokens is, I think, a much more advanced tokens in comparison with the location token. So I think you might also see more of these segmentations. Okay, so this is what a segmentation mask looks like. Okay, so instead of a bounding box, it outputs a kind of shaded area, which actually highlights or masks the object. So this is a segmentation area. So the question is now how to translate these sorts of tokens back to the image. So before you can kind of conceptually understand how to convert this segmentation token into the actual image, we have to first have a very short discussion, a very short introduction of the vector quantization variational autoencoder. So this we will be introduced this one properly in the image generation lecture. But for now, the vector quantization variational encoder is the middle part in here. So you see in this image, you have an image and you pass through a CNN. So instead of directly passing to the decoder, they actually formulate a set of predefined code. So this set of predefined codes will be mapped into a set of vectors. So you can view this as maybe you can understand this maybe say the text embedding. So when you're mapping text into a vector, this forces the image into a specified set of code. So with this set of code, you can pass through to the decoder. This have the advantage of designing this, so you can artificially design the code book in here, which now refers to also, you can also refer this as the embedding space. So you kind of find a expertly designed code book or expertly designed embedding. So we have this code book, and to convert this part into an actual area, we used also. Let's talk about how the model actually generates. So what's the actual output of the segment? So the Paragamma model will actually generate 16 of these tokens, each with a number of from 000 to 127, and using the decoded part of this quantized vector quantized variational autoencoder, it will map. It will decode it back to a 64 times 64 mask. Okay. So let's step through the process here. So for the for all the tokens, or the 16 tokens that will be generated by the Paragamma model, so each xxx is just an integer from 0 to 127. And these 16 numbers are flattened in a row measure model of a 4 times 4 latent grid. So token 1 will be in the grid position of 0, 0, 0, 0. Token 2 would be 0, 1, and so on and so on. So this 4 by 4 grid is the quantized latent representation of the original 64 by 64 binary mask. And there is a fixed code book with the 128 vectors shaded with 100. The dimension of the code book is 128 by D. So D is the embedding dimension. So for each 16 indexes, you will look up the corresponding vector. So by the end of this step, you will have a 4 by 4 by D feature map. Okay, and then with this map, you can just use the convolution neural network upsampling techniques that you have learned from last semester to reconstruct the 64 by 64 mask. And the output is a soft mask in the range of -1 to 1. Okay. And so besides the 64 by 64 mask, the size of the predicted bounding box, and you can paste this full image in the correct location. So by this is so for this image you have a bounding box and also the 64 by 64 mask. So within this bounding box, you have this part of the image colored, and you can map it back with the segmentation token. Okay, so in short summary, the polygamma model will output 16 of these tokens. Each of them corresponds to a number from 0 to 127, and it will look up the code book, and after looking up the code book, it will use a CNN to upsample the actual to upsample the 4x4 to 64 by 64 mask. And now you have a full resolution binary mask to mask out the object. Okay, so this is the output of the polygamma model. And after understand this, you can kind of use the model. And to use the model, what we meant by that is we actually want to perform inferences. So as I've said already, the polygamma model is a string prefix LM, so designed for structural tasks, and it has different modes to activate by specific prompt prefix. So we have all these kind of prefixes. You can read it, I think, at home. But in order to control the model using these task prefixes, you can use caption en. So caption means caption free text descriptions. You can answer English questions, which is just a short form answer. Tag class, whether it is in an image or not. So it will parse the location tokens and scale it. And of course, you can ask the model to segment task. And after the segmentation, it will output the segmentation token that we have discussed before. And of course, simple OCR task. So these are the prompts that you can actually put into the model. So it's kind of very different from an usual chatbot where you can just use English to communicate with the chatbot. So it is almost like a computer. So you have specific command, and you need to correctly input the correct token for you to interact with this type of model. So I think we have discussed about the conversion of location. So in order to interpret the segmentation, you also have to interpret the locations, and the location tokens ranging from 000 to 123. It is actually used to normalize the bounding box coordination in the task. It is written in a percentage form. So what I mean by percentage form is that if you have an image with the resolution of say 480 pixels, in order to decode this information, so actually finding the XY value, you have to divide this part to the scale and times the actual resolution, so that you can exactly get the X and Y direction in pixels. So the Model 3B consumes around 6 GB of VRAM, and it fits, I think, comfortably in, of course, our HPC server and also some edge devices. trade-offs if you're going to work with this model in the project. You might want to specify the device that you actually will run the project in. Okay. So these are the kind of use cases that you might want to try it out in your project. Say OCR in received OCR, advanced document recognizations. But of course, because the pedal OCR is already out last month, so for OCR specific tasks, you might want to use the pedal OCR instead of this one, this gamma model. And polygamma model, potentially you can deploy it in the browser, so you do not have to always call the API for simple tasks like object recognitions and say pressing button. You might have polygamma running in the browser for you. And some of the implementation error that many of the researchers have encountered is that sometimes you might forget to kind of put the separated tokens between the prompt and the output, and during training enforce the task and answer. So omitting it will make the model think the task description is still continuing. And I think many of, or at least me, I think because the /n token is always like it enter in the text editor. So sometimes when you format the data for you to train, you need to look out not actually this token, but actually entering the next line character. Okay. So there are some critics where polygamma actually breaks. So as we have mentioned, if you fine-tune it too much, it will kind of, this is not what the slide for. If you asking too many questions, it won't reply you because of the context window, and as well as the small, and as well as the cross attention mechanism is not that large. The context window is small, so it will forget what you have already asked. And for object detection hallucination, if the prompt that you ask is too complex, it might not actually achieve what you want. So if you want to ask for a complex task, say detect a keyboard on a desk, it might not work as well as only detect keyboards. So shorter is better. Okay. So it have no idea of left and right, okay, which is I think quite it's quite a I would say this, it do not have spatial purchase. So if you want to detect left and right, say if you want it to control an avatar, it might not be work that well. So what you can do is some kind of workaround, say detect the position of this at this kind of time frame, and also give it another window to detect it, and you compare it to recompute the directions. So for large images, it does not work that well because of it takes up around 50% of the context window for large images. So a workaround is to pre-divide the image into multiple patches of image and then feeding in each patch of image into the model. Of course, the filtering and safety. So you might want to detect whether there is a prompt injections or some other injections during the input. Okay, so there are other families of polygamma, polygamma 1, polygamma 2, and also gamma 3 and beyond. So you can incorporate different models, not only the gamma 2 that we have discussed, and with multi-modalities capabilities. Okay. So now we have go past all these 6 weeks, and hopefully by now you have a grasp of what your project might actually want to do. So we have discussed about the tokenization method and also matrix multiplication. And after that, we have discussed about LoRa. So you can fine-tune most model using this LoRa technique without paying the huge computation cost upfront. And we have discussed about how transformer can actually read images. And of course, I have swapped out this part with the pedal OCR because it's just out. So this part is a bit advanced, but I think if you really focus on the pedal OCR, you can maybe publish a paper or something. Because in week 5, the code in week 5 that I actually published, you can actually get some pretty nice fine-tuned results. And also so polygamma sort of use a bit of both. So you can use the vision encoder, the ziplet, and also the text generator, so they combine the two. Okay. So any questions for last week? So this is last week. So hopefully no question for last week. And so let's move on to this week. This week content. Okay, so let's change paces for a bit. So this week is the audio and speech processing week, and before so before we start, I think we will properly introduce machine learning. So I think what we have talked about is some architectures and also some training method and also some numerical ideas of how to train it. But I think it is a good point in time for us to actually discuss about the latest development and a conceptual understanding of AI as we noted. So, okay, so I was going to bring a coin in here, but I can't find a coin, so I will use a USB as a coin. So I will flip the coin, and I want you to vote so assuming this is head and this is tail. So if I flip a coin, let me just try to flip it.
0%.
Okay, so the shiny part is, I think, the head. The black part is the tail. So let me just flip a coin. This. Okay. So now what's the probability of the coin in my hand? So if you are saying it is 50, please raise your hand. 50. Okay, good. If you are saying it's either 0 or 10%, please raise your hand. Okay, 0. And for others, I assume that you don't know, right? Okay, so the answer for this is actually the Bayesian view of the world and also the frequentness of the world. So if you think about every event happen in this world, if you have not observed it as 50%, you are the frontier of AI. So because the frontier of AI treat every problem as a Bayesian view. So it treats every problem as a kind of probabilistic. Even if you have stack of data to kind of focus the coin flipping into either heads or tails. So I think the concept of this one related to the term KL divergence. So it is actually the cornerstone of current AI. So for all the models that you have learned related and all the so supervised learning, unsupervised learning, reinforcement learning, text recognitions, image generation, almost a video generation, text to speech, speech to text, all related to this fundamental idea, and which you should have known the last semester, but I will just do a quick recap in here. So the KL divergence covers every aspect of the machine learning and generative task. Okay. So I'm going to start very simple here. As you might have already learned, text embeddings and whatever embeddings is about distance, right? So comparing 2 points in the space is pretty simple, and of course comparing 2 ideas embedded in the text embedding is very simple. You just take a point, and then for the point, say x in here, point x, so P1 refers to the x dimension. P1 refers to the x dimension, and P2 refers to the y dimension. Computing this is very simple, but comparing distribution is a very different task. So probability distribution are not points, they are kind of describe patterns of uncertainties over many possible outcomes. It is, if you are, to put it in perspective, so let me give you a concrete example. So a probability distribution assigns a number between 0 and 1 to each possible outcome. So this number represents our degree of belief. In the coin flipping example, you would believe either the outcome is head or tails. That's why you put 50% and 50% to each outcome. So when you add the 50% head and 50% tail, it becomes 1. Okay. So Another example is that if there is a 70% chance of rain tomorrow, I believe in rain is 0.07. And of course, there is another view of probability. Probability is a long-running frequency of events over many repeated trials. So for those who believe in either 0 or 100% is the frequencies view. So you do not believe anything unless it happens. That's why you always need to look back retrospectively into the data. And the idea of frequentist is to compute the probability by the actual counts. But of course, the counting have to go to infinity for the frequentist view. So that's why frequentist is not a good kind of perspective, because you cannot sample everything to infinity. That's why the Bayesian view actually takes over the machine learning and also the AI that we have known today. So to summarize, tomorrow happens only once, but we can still assign the probability of 0.7 to rain based on our knowledge. And this works for any events, any unique events, any complex space, of course in high dimensions and also in neural network outputs. So probability actually represents the subjective certainty. So our degree of belief about any events, even if it is only happened once. So it happens in a uniform distribution, as we have talked about the coin flip, or the rolling of the dice, or the Gaussian distribution of human heights. And of course, in high dimension images. So say 10K dimension space describing all the possible pixel patterns. And machine learning works with distribution in space with millions of dimensions. And this is the cornerstone of image generation, like stable diffusion. And it also is the cornerstone of reinforcement learning. Okay. So it happens in this kind of concept used in classification generative models, reinforcement learning with human input, and knowledge distillation. So because today we are going to talk about voice generation, therefore I want to introduce it in this point, so that you know how the voice is actually generated. And to understand how the voice is generated, you need to understand the diffusion process, which is closely related to the KL divergence. So all of these uses KL divergence or cross entropy to measure how well a model matches the reality. Okay, so before we go any further technical into this topic, I want to have a definition with the surprised. So surprised is how unexpected the outcome is. So for the certain events, say for example the sun will rise tomorrow, we define this as a zero surprise. For rare events, say I win a lottery, this is a huge surprise. So in in here, from now on, we define surprise as the rare events that happens. So the more rare the event if it happens, the more surprise that we get. So we have to have some kind of rules when we're defining surprises. So what property should the surprise function we should have? It should have non-negativity. So surprise should never be negative. It should always be positive. And if the event is certain, so we want to have zero surprise by definition. And we want to have a monotone decreasing, so more likely events and less surprising. And also we want to add the surprise for independent events, like we want to have this additivity properties for us to have some kind of easier mathematical manipulation in the downwards operations. So there is exactly one continuous function that satisfies all four axioms. That is the log of the probability of the event. So if an event is very rare, the probability will be very low, and we'll be having a large surprise. And of course, multiplied by the constant c. So the surprise of the outcome of x becomes 1 over the probability. So if the event is very not likely to happen, this 1 over term will make it very large. And the log of 2 will kind of make this multiplicative events become additions. And also satisfying these other kind of properties. Personally, I think the reason they use log of the surprise is because of the additivity properties. Because it just find that easy to compute. Because one can define the surprise be 1 over the probability, the less likely the event will happen, the more surprise that I will get. But then you have to multiply all the probabilities together, because say if you roll a die 6 times, you have to multiply the probability by each one, and this makes the computation does not fit the neural network way of doing things. So they put a log in here to make this kind of, you can add and also subtract the surprises. So taking the negative log of px, just remove the 1 over terms in here. So for certain events, the surprise is, so for p is 1, so certain in here, the log of 1 is 0, so you have 0 surprises. And of course, the conflict is 1 bit, so 1 surprise. And if the probability is very rare, you have 6.6 bits, so the surprise getting larger. Okay, so after we have surprise, we want to measure how surprise of a series of outcomes that we will get from an actual event. Okay. So go back to this slide. Comparing this slide and this slide, what changed comparing this slide and this slide, what have changed? So what have actually changed? We actually just added the sum over all events against is likely to happen. So what this does is like asking what is the average surprise that we will get from the event that we are going to we are going to take. So if you go back to the conflicting events, 0.5 per, so 0.5 chance of getting either heads or tail. The conflicting is 0.5, so we will have 1 here, and 0.5 times 1 plus 0.5 times 1 would be 1. So we will have average surprise across all possible outcomes of the conflict is 1. So this is the definition of entropy. So entropy measures the inherent uncertainty, so baked it into the distribution. And for this term, this sum of all possible events, you can rewrite it using an expectation notation. So this rewriting allows the frequentist to actually do some sample against this surprise term. So the expectation of x using the probability distribution of this term, so will also can be also written as broken down events. Okay. So let's have some examples. So for 0-bit, when you are certain of an event, this part you will have no surprise of a certain event because all other events will be zeroed out. So if you think of, so this term will go down to 0 for all other terms. Because P of, say, cloudy is 0. So if you plug this in, so 0 multiplied by the log of 0 would be 0. And of course, the probability of rainy day would also be 0. So suppose the tomorrow weather is always sunny, so there will be no expectation. So the total number of surprise would be 0. So you do not have to look into the weather app because it's certain. And 0 average surprise. So every day brings out yes, no. And you already knew what is actually coming. Okay, from now, at this point I want to pause and I'll give you a break and take in any questions during the break. So if you have any questions, feel free to ask during the break. And I see you all very sleepy after this holiday, I think. So I think it's a good point for you.